All right, hello, physics students. Today, while I'm out, I want you to work on a couple of free fall applications. One of the things that I'd like you to finish before we practice a little more was that reaction time activity. If you remember, what we did is we dropped the ruler, it fell some height, and that's what we recorded down here. And we want to be able to convert that then to a reaction time. How many seconds, and it shouldn't be full seconds, right? How many maybe decimal seconds or fractions of a second did it take for us to catch that ruler? So let's back up and think about the physics involved here. So what we're doing is really nothing new, except we're looking at a different coordinate system. Instead of something horizontal, we're talking about something vertical. Horizontal, we used to say X marks the spot. Now we say Y marks the spot. So Y is the vertical position variable. If we use this as our coordinate system where the ground is the origin and positive positions are above the ground, so Y is greater than 0, then that means any motion upwards positive or is a positive displacement, and we would define that as a positive velocity. Any motion downwards is a negative displacement, and we define that as a negative velocity with this coordinate system. What we should have gotten out of the reading and some experiments is that the acceleration due to Earth's gravity is always, always, always downward. And we spent some time thinking about what this means. If I start off with a positive velocity, but a negative acceleration, that should make sense then. They're in opposite directions. When I launch or throw something up, the thing's slowing down. When it starts to fall back down, it now has a negative velocity and a negative acceleration. And if they're the same signs, that means the object is speeding back up. So the acceleration due to gravity never changes. In fact, it gets its special variable. We don't call it generic A anymore. We call it G. And G has a value. It's really, really close to 9.8 meters per second squared, right? And we found that out pretty close in our slow-mo lab when we were recording the thing in free fall. What does that mean for our equations? Well, we have this generic equation in terms of x's and acceleration that'll tell us how far or what's the displacement. That's delta x. And it looks like this. My initial velocity, so this should be initial, my starting velocity times the time plus this term, 1/2 at squared. That comes from, right, our curving shape for these graphs when something's accelerating. That parabolic shape is from t squared. When I want to adjust this for free fall, it's not new physics, it's not a new equation, it's just been specified for free fall. So now I talk about a distance above the ground, a displacement, delta y. I talk about a vertical starting position. So how fast do I throw something upwards? How fast do I throw something downwards? Or maybe I just drop it times the time. Because our acceleration is always downward, I took A, since it's downwards, and just distributed the minus sign. So it becomes minus 1/2 gt squared. This is a very useful equation for free fall. It tells us how high something is given its initial velocity and how long it's been in the air. We also then have this overall or general equation for velocity. It's just equal to your starting velocity plus the acceleration times the time you've been accelerating. Right? We've used that before. That's linear. Apply this specifically to the case of free fall. We get some velocity. It's equal to your starting velocity. Did I throw the thing up or down, or did I drop it? And then just minus gt. Right? So we're going to use this as well to talk about the speed or something's velocity in free fall. So let's turn our attention then to how do we use this information to find reaction times. You should have all of this populated, and remember what this is. This just gives you a height or a distance that something fell. And one thing we need to do is we need to be in meters. So if you record it in centimeters, make sure you put that thing back in meters. The first part's this, says simplified for this lab and with our new coordinate system, this equation becomes, well, we just did that a moment ago, and I'll rewrite it here. Delta y equals VIT minus 1/2 gt squared. So down here it says solve for time. Well, let's talk about it. This will actually simplify even a little bit more because we're dropping our rule meter stick. We're not throwing it upwards where VI would be positive. We're not throwing it downwards where VI would be negative. We're dropping it. So that means it's starting from rest. Vi is 0. So this term goes away, becomes 0. So simplified, this equation becomes this. Delta y equals minus 1/2 gt squared. Let's just think a little bit about, I got a minus sign here. Delta y, it's dropping. Should these numbers be not positive, or should these numbers be negative? They should be negative. They should be negative because they're falling downwards. That's important because we're ultimately going to take the square root, and we don't want to take the square root of a negative number. So these are going to be negative. I'm going to leave this for you. So this part here says solve for time. This equation becomes. So we need to solve this equation for time, because what we've measured is delta y, the displacement. That's how far the thing fell, and we want to get times out of it. So once you've done that, you're going to be able to do the backside. They're going to ask a few questions and make a few calculations for that. You're going to use these same equations here in your thinking on this kind of cartoonist worksheet that the substitute should have given you. So these are some general ideas about free fall speeds and how they change with acceleration, free fall distances and how those things might change, and some practice on the backside of doing displacements in heights. Okay? All right, so I will check your understanding when I get back on Monday. Bye, guys.